All right, so we finished up our first chapter of material dealing with linear equations and functions. So our next chapter, chapter 2, which you might expect, we kind of up the degree of difficulty a bit. So instead of talking about linear equations and linear functions, we're going to talk about quadratic equations and quadratic functions. So, it's not, unfortunately, it's not just kind of like a swap of the format. So we're going to start by talking about quadratic equations. The function stuff will come later. So the standard format for writing a quadratic equation is listed in there. So we're only going to have one variable in this guy for now. So we have ax squared. There's where the quadratic comes in. That is connected to that second power on that guy. So bx plus c equals 0. So we can have a term, we need to have a term with an x squared for it to be a quadratic equation. You'll notice it says that a, b, and c are fixed numbers. But we do require that a is non-zero, because if he goes away, then we're just dealing with a linear equation, and why do we give it a different name, right? So that's the general form. Note this particular arrangement is actually more important than it was when we talked about the general form for an equation for a line. You remember the ax plus by plus c equals 0 that I kind of poo-pooed on for the purposes of this course? We really do need it this time around. Unlike that linear equation, thing, we really do need it in this standard form for what we're going to be doing momentarily. So a couple of examples of these guys. If a, b, and c are all equal to 1, we could have just this guy right here. X squared plus x plus 1 equals 0. Now, as it turns out, we have to have the x squared term. The others could be absent. So this is also a perfectly valid quadratic equation. 9x squared minus 16 equals 0. That's also perfectly fine. I could write an x on the end of this and not have the constant term without an x at all. That's also still a quadratic equation. So those are a couple of examples here. So now, much like we saw with linear equations and linear functions, it's nice that we can just talk about them, but we probably, they're coming at us from some real world context, and we probably want a solution to the equation in question. So looking at the notes file for chapter 2, you have pulled that up, right? You got it handy. Okay. So there's two methods listed there. We're going to talk about the first method that's listed there, the factoring approach to solving a quadratic equation, for a bit in this video. For my money, though, past experience, I've taught this course several times at this stage. Generally speaking, most of my students find they end up preferring the second approach, so I don't want to, hopefully that doesn't foreshadow like where you just like stop watching this video now and jump straight to figuring out where I talk about method 2, or start like randomly clicking in the video to figure out where we are. But let's talk about this factoring approach first. So we basically want to try to figure out how to take a quadratic thing like this and split it up into a couple of linear pieces that'll look like a couple of mx plus b looking deals. And then, as it turns out, it's based on kind of this like core property of the real numbers as we know them. If you multiply two numbers together and they get 0, because the idea is this is broken into like an mx plus b thing times another mx plus b thing, and then it's equal to 0. Well, the idea is if you multiply together two things to get 0, the only way that happens is if one of them, was 0 in the first place. So that way you can sort of take each linear thing, set it equal to 0 separately, and then solve to see your potential solution values for the equation in question. All right, so there are 3 examples listed here. I'm planning on taking a look at 2 of them, and oddly enough, I'm skipping over the first one. Now, I've skipped over some first examples previously, because it was one of those, the later ones were harder and we could go back and do those. Actually, in this instance, I think the first problem in this example set is the hardest of the bunch. It's actually so hard that I don't even really recommend the factoring approach for that particular problem. So I generally would try to tackle that a little bit differently, But anyhow, let's go ahead and take a look at this second guy. So we start by throwing you for a loop and then using the variable y. Hopefully that's not too big a problem. So we have y plus 1 times y minus 5 equals 7. All right, so now our first order of business before trying to solve this thing is we actually need to get it into this format. We'll have y's instead of x's, but hopefully that's not too big a jump. Now, the challenge is it's not just a matter of subtracting over the 7 because we've got these two things multiplied together. So what I'm going to do is demonstrate one way of multiplying these guys out. It's something called the FOIL algorithm. You might have heard of it before. For multiplying these two things together, so you basically deal with kind of all of the distributive property, stuff that's required to get all of the right terms. So FOIL is an acronym that stands for first, outer, inner, last. So my first two terms are those guys right there. I multiply them together. Y times y gives me y squared. So I'll note that I'm using the FOIL algorithm there. Then I do the outer terms, the two guys on the outside, this y, this negative 5. So we have minus 5y. Then I do the inner terms. Those are these two guys right here. 1 times y just gives me y. If you'd written 1y, I wouldn't hold it against you. Plus y. And then I do the last, the two guys in the back of each of the two pieces I've got there. 1 times negative 5 gives me negative 5. This whole thing is still equal to 7. Now at this point, I can combine these y terms. I can't do anything to combine the y squared and the y to the first power. Don't do that. But I can also go ahead and move over this 7. So that would give me y squared minus 5y plus y is plus 4y minus 5 minus 7 is negative 12, and that equals 0. All right, and I did that wrong. Minus 5 plus 1. That should be a minus 4y. Heavens to Betsy. Okay, so there we go. That has the added benefit of being correct, right? So y squared minus 4y minus 12 equals 0. All right, from here, in terms of breaking this thing apart via factoring, there are all kinds of tricks out there. If you poke around online, you can probably get more elegant ways to do this, than what I'm doing, but this is sort of the way I've always learned it. Because the factoring approach, I think it works best when you have either a coefficient that's assumed to be 1, that's just y squared or x squared or whatever up front, or if the coefficient of that x squared term is a prime number. Because the idea is, if you want this to look like a couple of pieces like this bad boy, the only way we're going to get that y squared out of like a FOIL multiplication is if both of those guys lead off with just y. Okay, now you kind of have to play around a bit, and at this point, we know when we deal with these last numbers, we would get something that when we multiply them together, we'd get negative 12. So factors of 12, you could do like a 1 and a 12, a 2 and a 6, or a 3 and a 4, right? And since it's negative, we have to have like opposite signs. One is a negative, one is a positive. And if you play around with the possible options, the other big thing is that you'll notice we kind of added the two values together when we did this FOIL thing. So we need two numbers that multiply together to give us negative 12, and then add together to give us negative 4. Well, of our possibilities of those lists of factors I gave you, only one is actually going to fit that bill. We'd have y minus 6 and y plus 2. So again, if you repeat the FOIL algorithm multiplication here, you'd end up back at the guy that we've set up. So now we can take these two equations, set them separately equal to 0, because one of those two things has to happen. Whoops. Not y equals, y plus 2 equals 0. I'm getting ahead of myself because I've done this, I've done this an awful lot through the years. So now each of these is really easy to solve by itself, right? You may not even need the algebra operations. So y equals 6, because you add the 6 over, you just say 6 minus 6 is 0. The same thing here. We need y equals negative 2. So if you were asked for the solution set, kind of like we saw at the very beginning of chapter 1, it would look like 6, negative 2 in the curly braces. For my money, I'm also okay, like if you were writing this out by hand, just to like put a box or whatever around those two individual values. But the solution set WebAssign may ask you for it in like a comma separated list, so there you go. All right, so that's one example of this down. I've got time to take a look at example 3. Again, I am straight up punting on trying to do that first example using factoring. It's a hassle. All right, so let's take a look at this other guy. He is a little more challenging because it doesn't even look like a quadratic equation when you first look at it, right? You've got like these fractions and you don't see an x squared anywhere. So we have x over x minus 1 equals 2x plus 1 over x minus 1. Now the catch is, hopefully you remember this from what we were talking about in the previous chapter. When we've got the variables in a fraction, we're going to clear the denominators. So we're going to multiply by x minus 1, and then that gets rid of this denominator, that gets rid of that denominator. That guy is going to be 2x times x minus 1, because remember, we have to distribute that multiplication. So we have x, 2x times x minus 1 plus 1. And now I want to rearrange this thing into that ax squared plus bx plus c format. So distribute the 2x, subtract this x over, and we'll end up getting 2x squared minus 3x plus 1 equals 0. So now the factoring is a little bit trickier in this instance because we don't have just a leading coefficient of 1. But like I said, the next best thing is if the number in front of this x squared is a prime. So, because in order for that to work out, that's our only option. If we don't want like weird square roots or something. 2x times x gives us x squared. I guess we could write the 2 on the back, but potato, potato. We also need two numbers that multiply together to give us 1. There's really only two options, 2 positive ones or 2 negative ones. Since this guy in the middle is negative this time around, yeah, that kind of ends up indicating we need a pair of minus 1s in this instance. And again, if you check that via the FOIL algorithm or the box method or whatever you want to do, you'll end up getting 2x squared minus 3x plus 1. Lastly, now, just like we did before, I'm not going to write out setting each of these things equal to 0. You can kind of imagine, put this thing equal to 0 in your head and see what happens. Same deal right there. So 2x minus 1 being equal to 0, we do some algebra on that, we end up getting x equals 1/2, or maybe you just say, what number would make that happen? 1/2 works. Over here, x minus 1 equals 0, that feels a little easier. And you may notice, so there's our two possible solutions. So the solution said it might look like 1/2 1. But you might notice I kept saying might. It's kind of a weasel word. Remember, when we're dealing with fractional equations, we need to check to make sure each of these values could be plugged back into the original. And as it turns out, if you plug x equals 1 in here, survey says, as you say, we're trying to divide by 0 and that's bad. So he goes bye-bye. X equals 1 off the table. This is our only solution this time around, or if you wanted to write it in the set format, 1/2. All right. So that's the factoring approach to solving quadratic equations. So I've already sort of let the cat out of the bag. A lot of my students prefer what's going to come next, but in instances where this first term, like I said, is a 1 or that coefficient is a 1 or a prime number, it works out pretty well. I don't want to downplay it. It's just that like in that first example where you have lots of different factorizations to take into account, figuring out how to break it up can be a problem. All right, so we'll take a look at that other approach for solving quadratic equations in our next video.